in this video, what we really want to emphasize is how to approach these problems where you are given a starting condition or initial condition, and after some amount of time you hit equilibrium, and naturally your concentrations are going to change. Right? It's very unlikely that you start at equilibrium, and we want to know how they're going to change. We want to be able to determine the concentration at equilibrium from our initial condition, or determine our initial condition from our equilibrium properties. So we're going to go ahead and dive in. The method is called ICE because it stands for initial, change, and equilibrium. So when we're doing a problem, such as this one here, what we're going to do is we're going to make a little table, which is ICE in the leftmost column. That. And then we're going to have our reactants first. So CO2, and then if we get another reactant, it would be the next column. But we don't, so then we're going to have our products, which is going to be carbon monoxide and chlorine gas. Okay. And so what we're going to do, erase some excess stuff here. So we're going to fill out this table with the information we know, and then identify what we're looking for. So it's initially full of this at 5 molarity. So we're going to say this is 5 molarity. And so if it's initially full of COCl2, then that means our concentration here and our concentration here are both going to be 0. So these are 3 things that we know initially. Now, in order to determine the other 2, we're going to need some more information. So for the change, we can say that the change in COCl2 is going to be negative X. And essentially what that means is for every 1 molecule of COCl2 which decomposes, you're going to have plus 1 molecule of carbon monoxide and plus 1 molecule of chlorine gas. So the coefficients in our reaction equation determine the coefficients in front of our change, or in front of this X term. So here they're all 1. We'll do an example later where they're not all 1, they're actually all a different number. We'll see how that kind of plays in. But for here, what we can do now is equilibrium is going to be equal to our initial plus our change. So here we're going to have 5 plus negative X. It's going to be 5 minus X. Our carbon monoxide is going to just be X. Same with our chlorine. Now if we come over here, we'll see that our KEQ has been given. And if you remember, KEQ, as the EQ denotes, is the equilibrium constant. It's the constant at equilibrium. So if we write out the equation for it, it's going to equal concentration of carbon monoxide, chlorine, all over COCl2. Okay? Excellent. So we have this, and we know that this equilibrium constant only applies for these values, right? If we did it here, we wouldn't get the equilibrium constant, we get our reaction quotient, which would tell us which way our reaction is going. But that's pretty obvious. If we start with reactants, then obviously it's going to shift to the right. So we're going to come down here, and we're going to plug in our equilibrium values into this equation. So we're going to end up with KEQ, which is going to be 170, is equal to X times X over 5 minus X. Alright, I just substituted in the concentrations here. So then if I rearrange this, I'm going to get X squared is equal to 850 minus 170X. Rearrange slightly and you get X squared plus 170 minus 850 is equal to 0. So you can solve this using the quadratic formula. For the person who loves math, you'll know that the quadratic formula will give you 2 answers. One of them will be positive, one of them will be negative. Having a negative X is meaningless because, as you can see here, if we start at 0 and then we have a negative X, then we're essentially destroying something or reducing something which doesn't exist. So that's obviously physically impossible. So even though the math says it should be, it is not. So we're going to ignore the negative number and just say it's unphysical, which leaves us with our positive number, which comes out to be 4.86. Okay, Now we come over here, and wherever we see x, we can replace it with 4.86. So I'm going to leave the x's in the change row and just look at the equilibrium. So this is now going to be 4.86. This is going to be 4.86. And this, 25 minus 4.86, or 0.14 molarity. So, in order to answer our question, what are the concentrations of carbon dioxide and chlorine gas in equilibrium? Well, they're both 4.86 molarity. Okay. And so hopefully you can already start to see how this ICE method makes things much simpler, right? We're able to identify our starting conditions. We're able to systematically describe how things are going to change, even if we don't necessarily know the number. And then finally, we're able to look at what our final equilibrium concentration is, first symbolically, because we don't know the number. And then using our relationship with our equilibrium constant, we're actually able to calculate what the change will be, thereby granting us the ability to calculate our concentration of our equilibrium.